The research paper delves into the complexity of simple folding for mixed orthogonal crease patterns, building upon previous studies on foldability problems for 1D and 2D rectangular paper with different models of simple folds. It presents new efficient algorithms for mixed crease patterns in 1D cases and for 2D rectangular paper with one-layer simple folds. However, the authors also demonstrate strong NP-completeness for mixed orthogonal crease patterns on 2D rectangular paper with some layers simple folds and for unassigned orthogonal crease patterns on arbitrary paper with finite simple folds. This work provides a comprehensive characterization of polynomial versus n-fard cases for various foldability scenarios, except for the case of infinite layers simple folds of assigned orthogonal crease patterns on arbitrary paper, which remains unsolved. This page presents a comprehensive summary of prior results and new findings regarding simple folding orthogonal crease patterns on various paper shapes. The complexity of these problems is examined based on two primary parameters: whether some creases are assigned as needing to be folded mountain or valley, and the allowed shape of the paper. The paper considers exclusively orthogonal crease patterns, which contain only vertical and horizontal creases, and explores the complexities of problems with assigned, unassigned, and mixed crease patterns on 1D, rectangular, and arbitrary paper shapes. Table 1 provides a concise summary of the known complexities, including previously established results and new findings from this paper. The new results can be summarized as follows. The authors adapt arguments from prior work to provide novel characterizations of when a 1D assigned or mixed crease pattern is flat foldable. Specifically, they examine one and some layers mixed 1D cases, as well as one-layer mixed rectangular cases, and show that crossing creases can never be folded on rectangular paper, reducing the problem to 1D paper. The authors also highlight the distinction between finite and infinite simple folds, noting that this distinction only plays a role in the case of arbitrary paper, with no distinction possible in the 1D case and equivalence established for rectangular paper by prior work. The implications of these results are immediate from containment, denoted by subset of, and rightwards double arrow symbols, which represent the relationships between the different problem classes. The paper presents new results on the foldability of crease patterns in various models. A greedy strategy is proposed for a layers mixed 1D crease patterns, where simple foldability is decided by folding the superficially foldable crease nearest an end of the paper, preserving the foldability of the crease pattern. In the some layers mixed rectangular model, the NP hardness reduction from previous work is shown to apply, implying that deciding foldability in this model is computationally intractable. For unassigned arbitrary finite crease patterns, the NP hardness proof from previous work is modified to enforce the relevant aspects of the assignment, fixing a bug in the original reduction. This result applies to any number of layers. The only remaining unsolved case for orthogonal crease patterns is infinite layers simple folds of assigned crease patterns on arbitrary paper. The paper focuses on 1D paper and mixed assignment, one and some layers folds. A new characterization of which 1D assigned crease patterns are foldable in the one or some layers models is presented. This characterization is then extended to 1D mixed assignment one and some layers crease patterns. In the 1D crease pattern model, a horizontal line segment represents the paper, with a finite set of points on the paper denoting creases. The paper has two endpoints, referred to as ends, and together, creases and ends are vertices. An interval between two vertices has up to two flaps, and an interval is interior if neither of its endpoints are ends of the paper. A function f maps the paper to its folded state geometry by alternating going left and right. An interior interval is suspicious if the images of its flaps' far endpoints are both strictly outside the image of the interval in the folded state. An innocent interval is one where the numbers of mountain creases and valley creases differ by at most plus or minus 1. The new characterization of flat foldability is based on these concepts, providing a polynomial time approach to deciding foldability in the 1D mixed assignment one and some layers models. The concept of suspicious innocent intervals in crease patterns is a crucial aspect of flat foldability. These intervals are characterized by their unique characteristics, which include the presence of crimps and end folds. Crimps and end folds play a pivotal role in proving the equivalence of different conditions for flat foldability, such as the ability to be folded by one layer or some layers simple folds, and the innocence of all suspicious intervals. The proof for this equivalence involves a cycle of implications, starting from the ability to be folded by crimps and end folds. This cycle demonstrates that each condition implies the next, ultimately concluding with the innocence of all suspicious intervals. This means that if a crease pattern can be folded using crimps and end folds, it also meets the other conditions necessary for flat foldability. The significance of suspicious innocent intervals lies in their potential to affect the overall flat foldability of a crease pattern. By understanding these intervals and their characteristics, researchers can better design and analyze crease patterns for various applications, including origami, engineering, and materials science. In summary, the concept of suspicious innocent intervals in crease patterns is essential for understanding flat foldability. The use of crimps and end folds provides a framework for proving the equivalence of different conditions for flat foldability, ultimately leading to the innocence of all suspicious intervals. This knowledge has implications for a wide range of fields where crease patterns are utilized. In this section, the authors delve into the relationship between suspicious intervals and crimps in the context of flat foldings. They begin by proving that if all suspicious intervals are innocent, then there must exist a segment that is either crimpable or end-foldable. This is achieved through a series of logical steps involving the consideration of shortest segments in the crease pattern and their relation to endpoints and equal-length segments. The authors then proceed to demonstrate that performing a crimp preserves the property of every suspicious interval being innocent. This is shown by examining the effects of a crimp on the paper's geometry and crease pattern, with particular attention given to the transformation of suspicious intervals and their flaps. In the case where the new segment formed by the crimp contains the suspicious interval, it is shown that the crimp does not alter the image of the interval or its flaps in the folded state, thus maintaining the innocence of the interval. In the case where the new segment is a flap of the suspicious interval, the authors demonstrate that the crimp also preserves the innocence of the interval by analyzing how the vertices involved relate to the interval in the folded state. These results contribute to the broader understanding of flat foldings and their properties, shedding light on the interplay between crease patterns, suspicious intervals, and crimps. The technical details provided in this section serve as a foundation for further exploration into the geometric and combinatorial aspects of paper folding. In the realm of origami theory, this page delves into the implications of crimp and endfold operations on the flat foldability of mixed 1D crease patterns. The core concept explored is the notion of suspicious and innocent intervals within these crease patterns. A suspicious interval is defined as a subinterval of a crease pattern where the number of mountain and valley creases differ by at least 2. An interval is considered innocent if it does not contain any suspicious subintervals. The main theorem, Theorem 2.1, states that a crease pattern is flat-foldable if and only if every suspicious interval is innocent. The proof of this theorem involves showing that performing a crimp or endfold operation preserves the innocence of suspicious intervals. A crimp is a specific type of fold that involves bending the paper along a crease, creating a new vertex, and then bending the paper back along another crease to create a new face. An endfold, on the other hand, involves folding the paper along a crease that lies at one end of the pattern, effectively deleting the leftmost segment of the crease pattern. Lemmas 2.3 and 2.4 demonstrate that both crimp and endfold operations maintain the innocence of suspicious intervals. This is achieved by analyzing different cases for the location of the crimp or endfold relative to the suspicious interval in question. In each case, it is shown that either the original suspicious interval remains innocent or a new suspicious interval emerges, which can then be addressed through further crimp or endfold operations. The process of identifying and resolving suspicious intervals continues until no more such intervals remain, at which point the crease pattern is deemed flat-foldable. This process forms the basis for a polynomial time algorithm to determine the flat foldability of mixed 1D crease patterns, as discussed in the subsequent section of the paper. The algorithm for determining whether a given 1D mixed crease pattern has a valid assignment and finding one if it exists is presented in Theorem 2.5. This theorem is pivotal in origami, where the assignment of creases significantly impacts the final folded structure. The proof involves 3 main steps. First, all suspicious intervals are identified by checking all pairs of creases, resulting in a quadratic number of checks. Then, for each suspicious interval from smallest to largest, the algorithm assigns all or all but one still unassigned crease within the interval to guarantee its innocence and preserve the existence of a valid assignment. If no valid assignment can be found, the algorithm terminates and reports that there is no valid assignment. The remaining creases are assigned arbitrarily, and the resulting valid assignment is returned. A key component is the concept of minimal suspicious intervals, which are intervals that contain no smaller suspicious intervals that have not yet been fully assigned. The algorithm checks if the unassigned creases can be divided into an equal number of mountain and valley creases, ensuring the interval's innocence. If such an assignment is possible, it is used. Otherwise, the algorithm terminates and reports that there is no valid assignment. The case of a suspicious interval with an odd number of creases is also considered, where it checks if excluding one unassigned crease and finding an assignment on the rest can make the interval innocent. If this is possible, the excluded crease remains unassigned, and the other creases are assigned accordingly. If not, the algorithm assigns all creases in the interval to make it innocent, which happens when there are k+1 previously assigned creases of one sign. The validity of the algorithm is supported by Lemma 2.7, which states that assigning creases for a single minimal suspicious interval as described in the algorithm preserves the existence of a valid assignment. This ensures that the algorithm's steps do not inadvertently create new issues or conflicts with previous assignments, thereby maintaining the overall validity of the crease pattern. The theorem provides a crucial contribution to the study of origami by offering a polynomial time algorithm for determining and finding valid assignments in 1D mixed crease patterns. The proof of Theorem 2.5 is presented, demonstrating that the algorithm can find a flat foldable assignment for a mixed crease pattern in polynomial time. This is achieved by constructing an assignment A+ that extends AI, agreeing with A+ everywhere except with an interval I, and assigning the same number of mountains and valleys to I as A+. By flipping the assignment of creases in A+ that do not agree with AI, A+ and AI are shown to agree on mountain and valley counts. The validity of A+ is established by demonstrating that every suspicious interval J is innocent in A+. The running time of the algorithm is analyzed, with step 1 requiring O, n3, time, step 2 requiring O, n3, time, and step 3 requiring O, n, time. Theorem 2.5 is then used to prove corollaries 2.8 and 2.9, which state that it is possible to determine in polynomial time whether a mixed 1D crease pattern can be folded flat using one layer's simple folds or some layer's simple folds, respectively. Furthermore, corollary 2.10 is proven, extending corollary 2.8 to rectangular paper. This result is established by observing that an orthogonal crease pattern on rectangular paper with both horizontal and vertical creases is never flat foldable in the one-layer model. In contrast, a crease pattern with only one direction of creases is equivalent to a 1D mixed crease pattern and can be solved using the algorithm from Theorem 2.5. This highlights the significance of the algorithm in determining flat foldability for various types of crease patterns and paper shapes. In the A-layers model of simple folding, the authors propose a polynomial time greedy algorithm for mixed 1D crease patterns. This model assumes that layers cannot be separated once they come into contact, effectively gluing the paper together where it overlaps. A valid fold in 1D must fold each valley or mountain crease onto a mountain or valley crease, or an unassigned crease, or a point not interior to the paper. Folding a crease onto a non-vertex point of paper or a crease with an incompatible assignment would prevent future A-layers folding of the crease. The simple greedy algorithm, which involves performing any valid fold at each step, can fail in the mixed case where creases have both assigned and unassigned values. This is because folding an assigned crease onto an unassigned crease effectively causes it to become assigned, and a foldable crease pattern can become unfoldable after making a valid fold. To address this issue, the authors propose a refined greedy algorithm that considers plausible creases. A crease P is plausible if the locations of creases, ignoring assignment, are symmetric around P up to the nearest end of the paper. Figure 3 illustrates examples of plausible creases, marked with arrows. Lemma 3.1 provides a key insight into the structure of foldable crease patterns, stating that if there is a sequence of valid A-layers folds that folds the crease pattern, then there is such a sequence that folds the plausible crease with minimum distance to an end of the paper first. This lemma serves as a foundation for the refined greedy algorithm, offering a more efficient approach to solving the mixed 1D crease pattern problem in the Allaire's model. The authors present a proof for Theorem 3.2, which states that there exists a polynomial time algorithm to determine whether a 1D mixed crease pattern can be folded using Allaire's simple folds. They begin by assuming, without loss of generality, that the plausible crease P is located on the left half of the paper, including the midpoint. The authors then consider the open interval IP of length 2D centered at P, where D is the distance from P to the left end of the paper. They suppose that a valid Allaire's folding sequence F equals F1, F2, Fn is given, where each phi folds one crease in the current reduced folding sequence. They identify the first fold phi in F that folds a crease in IP, and let Q be the crease in IP folded by phi. By restricting attention to the paper in IP, the authors argue that Q must be foldable in the original crease pattern as well, and therefore Q must be plausible when considering the crease pattern restricted to IP. Using the symmetry of the creases in IP around P, the authors show that the reflection Q of Q across P is also plausible within IP. If Q does not equal P, then one of Q and Q lies to the left of P, contradicting the assumption that P is the leftmost plausible crease. Therefore, Q equals P, and the first fold phi in IP is at P. The authors then argue that the folding sequence F induces a mountain-valley assignment for all creases, and that this assignment restricted to IP is antisymmetric when reflected across P. Therefore, P is a valid fold in this fully assigned crease pattern, and there exists a valid sequence of Allaire's folds that folds P first. The authors note that the plausible crease P in lemma 3.1 might not be valid, but in this case, they can deduce that the crease pattern cannot be folded using Allaire's simple folds. This leads to a refined greedy algorithm: repeatedly find and fold, if possible, the plausible crease nearest an end. Determining whether a mixed orthogonal crease pattern on rectangular paper can be folded in the sumlayers model is NP-complete. This contrasts with the polynomial time algorithm for the one-layer model. The proof adapts the reduction from AAB plus 2O, section 5, which demonstrates NP hardness for the Allaire's model. The key insight is that instances never permit unintended foldings when relaxing to the sumlayers model. A crucial lemma is established, stating that if a simple fold is made in an orthogonal crease pattern with rectangular paper, and it is not in the same direction as the previous fold, it must be an Allaire's fold. This lemma is proven by induction. The theorem then follows, concluding that determining whether a mixed orthogonal crease pattern on rectangular paper can be folded in the sumlayers model is NP-complete. The significance of this result lies in its distinction from the one-layer model, where a polynomial time algorithm exists. The NP-completeness of the sumlayers model highlights the complexity of folding mixed orthogonal crease patterns on rectangular paper. This has implications for the study of origami and its applications in engineering, computer science, and materials science. The figure illustrates a reduction from 3 SAT to Allaire's simple foldability of mixed assignment orthogonal crease patterns on rectangular paper, corresponding to the Boolean formula, x1 or x2 or x3, or x1 or x2 or x3. This setup is achieved by dividing the paper into a square grid of creases, with each section corresponding to a variable. The lower part of a variable section contains valley creases for each variable occurrence in a clause, and the upper part contains mountain creases for positive or negative literals. A topmost section checks clause satisfiability, and assigned creases enforce the variable order. This setup enables the evaluation of Boolean formulas through paper folding, demonstrating a novel application of origami in computational complexity theory. The reduction process involves assigning true or false values to variables by folding adjacent creases, determining the assignment of the variable. This process is done in a specific order, with each variable's creases being folded in a particular sequence to ensure correct clause folding. Valley folds and mountain folds are crucial to prevent other foldings and ensure variable assignments. After the variable folding stage, clauses must also be folded, requiring all layers of the paper due to alternating vertical and horizontal folds. This leads to a degree 4 vertex with all valley assignments, making it impossible to fold the paper in the sum-layers model. The authors then discuss the NP-completeness of determining whether an unassigned or assigned orthogonal crease pattern on arbitrary 2D paper has a simple folding. They modify the construction from AdK17 to reduce 3 partition to the assigned problem, fixing a bug in the original reduction. The original reduction consists of 6 parts: the bar, the staircase, the wrapper, the column, the cage, and the arm. Each component plays a critical role in the reduction, setting the stage for the author's proof of NP-completeness in the subsequent sections. The buggy reduction from 3 partition to assigned orthogonal crease pattern simple foldability with arbitrary paper is illustrated in Figure 6. This construction involves passing the bar through the cage without collision when folding 2 creases on the wrapper. The vertical position of the bar must align with the staircases in the cage, requiring each successive step to be 2 units higher than the previous one. This necessitates a total length of segments in the staircase to be folded each time, achievable only if the 3 partition instance has a solution. One step of folding the bar through the cage after crimping 2t total height of the staircase segments is demonstrated in Figure 7. However, an unintended folding pattern, shown in Figure 8, bypasses the intended alignment, undermining the original purpose of the construction. The mathematical expressions, such as infinity 2 trillion, 3 and 2t, n1, 3, are crucial for understanding the geometric transformations and spatial relationships involved in the folding process. These equations determine the required lengths and positions of the various components within the construction. The importance of maintaining the integrity of the original design is highlighted, as unintended folding patterns, like the one in Figure 8, could lead to incorrect or incomplete solutions to the 3-partition problem. This emphasizes the need for careful consideration of all possible folding scenarios during the design phase. The buggy reduction technique's intricacies and its application to solving the 3-partition problem using origami principles are discussed, emphasizing the significance of precise geometric calculations and careful design to prevent unintended folding patterns that might compromise the solution's accuracy. The process of implementing a 3-partition solution involves the folding of the bar and the cage. It is crucial to correctly fold the bar along the wrapper crease to avoid overlapping with the cage. To resolve this issue, the concept of folding a horizontal valley crease in the staircase is introduced. This technique enables the continuation of the folding process without encountering the overlap problem. The discussion then shifts to the assigned reduction, where a modified proof is presented for Theorem 5.1. This involves adding an additional arm above the wrapper to prevent the bad behavior depicted in Figure 8. Figures 9 and 10 illustrate how the new arm 2 prevents the valley fold in the staircase, ensuring a smooth folding process. This section delves into the complexities of unintended folding and unassigned reduction in the context of orthogonal crease patterns on arbitrary or orthogonal paper. It begins by illustrating unintended folding, which disrupts the reduction demonstrated in Figures 6 and 7 through Figure 8. This figure showcases a sequence of 5 folds, with the axes of these folds highlighted in dashed blue and red lines. The folds involve staircase creases and wrapper creases, resulting in the bar colliding with the cage unless they are precisely aligned. The authors then modify the proof to address the unassigned case, presenting Theorem 5.2. This theorem states that it is NP-complete to determine whether an unassigned orthogonal crease pattern on arbitrary or orthogonal paper can be folded in each of the one-layer, some-layers, and a-layers models. The proof builds upon the work of Akitaya et al., AdK17, who demonstrated that the only necessary assignments are those on the wrapper, which must be all valley or all mountain. The authors argue that the assignment of creases on the staircase is irrelevant, as altering the assignment does not affect the foldability of the construction. The uniform assignment of the wrapper forces all creases on the wrapper to be folded in order from right to left, ensuring that the bar passes through the cage at each step, thereby checking the 3-partition instance satisfaction. The authors adapt the approach of AdK17 to utilize unassigned orthogonal creases and particularly shaped paper to achieve this, rather than relying on unassigned 45-degree creases. Overall, this section contributes to the paper's exploration of the complexity of folding orthogonal crease patterns, highlighting the challenges of unintended folding and the nuances of unassigned reduction. Figure 9 illustrates the reduction from 3-partition to assigned orthogonal crease pattern simple foldability with arbitrary paper, building upon the concept introduced in Figure 6. This reduction is facilitated by the cactus construction, depicted in Figure 11, which features short branches of paper, denoted as IO, situated before each crease C. These branches ensure that creases are folded in an increasing order, starting with C0, by preventing the intersection of paper folds. Specifically, if any paper connected to the opposite side of C is folded on top of IO, C cannot be folded, as this would cause the paper to intersect itself. The alignment of the cactus's branches is crucial, as it guarantees that whenever C is folded, the previous branch IO1 will be aligned with the next branch IO plus 1. This alignment makes it impossible to fold C1, thereby ensuring the validity of the folding process. The cactus construction is a key component in reducing 3-partition to assigned orthogonal crease pattern simple foldability, enabling the exploration of complex folding patterns with arbitrary paper. The intricate relationships between the creases, branches, and paper folds are highlighted in Figure 9. Demonstrating the author's novel approach to tackling the assigned orthogonal crease pattern simple foldability problem. The careful design of the cactus and its branches underpins the reduction, allowing for a deeper understanding of the folding process and its constraints. This reduction has significant implications for the study of assigned orthogonal crease pattern simple foldability, providing a foundation for further research into complex folding patterns. The development of a novel origami model, as discussed in this research paper, introduces an innovative design element called the cactus. This component replaces the traditional wrapper in origami models and enforces a right-to-left fold order on creases, ensuring they are all folded in the same direction. The cactus consists of arms sticking out from its body, forcing creases to be folded in a specific order. For instance, if crease C1 is folded before crease C0, it would cause A2 and A0 to overlap, preventing C0 from folding without collision. Thus, the cactus ensures that crease C must be folded before C1, respecting the intended order. Arm 1 plays a crucial role in maintaining the uniformity of the wrapper's crease direction. Assuming the order of these creases is already forced by the cactus, Arm 1 ensures that all unassigned creases on the wrapper are either mountain or valley creases when folded from right to left. This uniformity is essential for preventing collisions and achieving the desired geometry in the final structure. Figure 10 illustrates the intended folding sequence for the new reduction in Figure 9, including the addition of Arm 2 and the highlighted column. This sequence involves crimping variables to change the height of the bar by 2t, folding along the rightmost wrapper crease around the column, fitting the bar through the cage while folding the bar to the left along the next wrapper crease, and repeating this process until n3 triples have been checked. In conclusion, this research paper highlights the innovative cactus construction and its role in enforcing a specific fold order and uniform crease direction in origami models. It also demonstrates how this new design element can be applied to achieve precise control over geometry in complex structures. The proof of NP hardness for unassigned 45-degree creases utilizes the bar and cage structures, emphasizing the crucial role of arms 1 and 2 in ensuring correct fold assignments. This leads to a situation where no further folds are possible. The discussion then shifts to open problems, particularly infinite layers simple folds of assigned crease patterns on arbitrary or orthogonal pieces of paper. Two approaches are presented. One attempting to mimic the reduction from the rectangular mixed assignment problem, and another focusing on reducing to the rectangular fully assigned problem. Both approaches face challenges, highlighting the complexity of the problem. In geometric folding algorithms, foldability is a critical concept that ensures the feasibility of a folding pattern. A key aspect of foldability is the safety of creases, which can significantly impact the unfoldability of a pattern. Figure 1 illustrates a foldable pattern where the horizontal crease appears safe, but in reality, it makes the pattern unfoldable. This highlights the importance of careful consideration in crease placement to maintain foldability. In contrast, Figure 2 presents a pattern that seems safe when evaluated under 1D mixed foldability but becomes problematic upon actual folding. This demonstrates that even seemingly safe patterns can still exhibit issues, emphasizing the need for rigorous testing and analysis. The development of these insights was facilitated by the contributions of participants in an MIT class on geometric folding algorithms, where this research was initiated. The importance of productive discussions and a conducive research environment cannot be overstated, as they enabled the exploration of these critical aspects of foldability.